With the emergence of consumer products with stereo and depth camera, a large amount of animated time-dependent point cloud data can be collected without much effort. Such data is on the one hand highly redundant and on the other hand incomplete, typically due to occlusion. So our goal is to develop algorithms that can do both data compression and completion. And the solution proposed in this work is to find suitable low-dimensional representations for them. There are several challenges. First, animations can be in a state of fast deformations and movements. Second, it can have a large portion of missing data, for example, parts not facing the camera, in which case missing data will be structured. Challenging fast movements suggests that the problem can be solved only as a global optimization, which lays additional obstacle when it comes to practical implementation that does not computationally explode with the number of point tracks and the growing length of the animation. Existing methods approach this problem in different ways. There has been a lot of work on the non-rigid reconstruction from 2D point tracks, which formulate the problem as matrix factorization. Due to the problem of finding suitable data source, they are proposed for 2D point tracks and can recover non-causal correlations such as the left arm and the right leg for a walking person. Many works were on finding the most suitable reconstruction error term and regularizer. However, it has been shown that the method performs poorly if missing data is structured, as in our case. Ensemble models are proposed to tackle this problem, yet to avoid overfitting, models need to be very simple, and they are generally computationally expensive. Some other researchers focus on the non-rigid reconstruction by iterative warping of estimated geometry into the life frame, yet only applicable to slow trackable movements with perceived fixed topology. Tracking-based methods can track moving objects but require manual initialization of the first frame, and deep learning-based approaches are data-driven and not suitable for novel characters decomposition. We propose a novel method that can distinguish body parts and factor the data into shape and pose purely using topological properties of the manifold, local neighborhoods, and their deformation. To obtain such localized factorization, we formulate the deformation distance between 2 point tracks as the smallest deformation along the path between them. After embedding such distance in low-dimensional space, a clustering of embedded data leads to close-to-rigid components, suitable as initialization for fitting a model, a skin-rig mesh used extensively in computer graphics applications for deformable objects. We show how to estimate all its components, a static mesh, a set of limbs, the transformation matrix in each frame, and the association of points and weights with each limb. Both inputs of the method, local deformations and the neighborhood of a point, are local, and thus can be estimated only from the part of the animation, where each point is observable. This makes the algorithm applicable to the presence of missing data and can be used for the completion of 3D point tracks. We applied our method on artificial computer graphics models and real-world captured data, and demonstrate that the method works robustly in both cases. Let's look at the steps one by one. The first step is to derive the deformation matrix. In our case, the relationship between a pair of points is classified into 2 categories: neighbors, for which distance stays within a threshold during the whole animation, and non-neighbors. For neighboring points, their distance is defined to be the summation of distance between the transformation matrix of each point over a sequence of randomly chosen frame pairs, which accounts for the transformation of the greatest number of points of the points of interest. Practically, it is calculated using RANSAC, and the distance between non-neighboring points is defined to be the length of the shortest path between them. This step results in the deformation matrix. After calculating this matrix, we proceed to calculate the low-dimensional embedding of point tracks. We aim at an embedding whose Euclidean distance approximates the deformation distance, which can be formulated as isomap dimensionality reduction. Thus, algorithms for that apply. After performing double centering, the m-dimensional embedding is recovered using m eigenvectors corresponding to the m largest eigenvalues. Notice that technique of landmark isomap can be deployed to improve computational efficiency. One important observation in our distance measure is that for points apparently transforming rigidly, the distance between them should be small. And since the Euclidean distance between low-dimensional embedding encodes the deformation distance, we can perform clustering to get a set of rigid limbs. Many clustering methods can be potential candidates, and in our case, we choose the combination of extreme values to be the clustering criteria. Until this stage, points are grouped to form a set of rigid limbs, and we'll proceed to assign points to possible multiple clusters to form a rigged mesh model. For each cluster, we maintain a static template that is initialized to be the starting position of each cluster. We update it incrementally. For each frame, we calculate the alignment using a ransack again to derive a matrix that describes the transformation from the current frame to the static template of the most points in the clusters. Then, we update the static template by setting it to be the average of the calculated position. For quality improvement, several iterations can be conducted. We let the transformation sequence calculated to represent the transformation of each cluster and reassign points to clusters best jointly describe its transformation. Mathematically, it can be formulated as a least square problem under constraints that the weights should be non-negative and should add up to 1. In practice, use the top 3 limbs would be sufficient. For the task of 3D data completion, the above pipeline is almost immediately applicable with minor alternations. Since only local features are considered, it can be naturally extended to be compatible with the data completion task. Neighboring criteria should be adjusted to only consider distance in visible frames. The deformation measurements for neighbors is adjusted to be the average distance between the transformation matrix. And the template updating and the transformation matrix calculation is modified to only take visible points into account. We carried out both experiments of data compression and completion on artificial data and real-world data, and compared them with previous work in terms of normalized reconstruction errors. Results verify that our methods work surprisingly well, with a slight exception on data from fat people, which require more clusters to independently model belly and back. The average reconstruction error is only approximately twice that of complete data. Here, you can find more results in data compression and completion. Afterwards, we also tested the robustness of the model by adding Gaussian noise to the input. One can observe from the table that with the increase of noise level, the error between noise-free ground truth and reconstruction converges to the level of noise, which indicates its resilience to a certain level of noise in the input. That's all I want to share today. Thanks for listening.